Start recording now. Awesome. Okay. So you can title these circular motion basics, and we have a definition for circular motion that says an object in circular motion is acted on by a continuous net force that's directed towards the center of the circle. And that probably doesn't make a lot of sense to you. I know that when I first started learning about this, I really struggled with this idea of what is a continuous net force? And how does it push something towards the center of the circle? In my mind, that thing, if it's pushing continuously towards the center of the circle, isn't that going to make a spiral? How could it make something that would go in a perfectly circular path? So, write down this definition, and then we'll talk about, and I will give you an example. Also, I will put the notes on Canvas so that if you can't keep up with the notes, you'll be able to access them there as well. So, like I said, when I first started learning about this, it was very confusing to me. I'm thinking a continuous force towards the center of the circle, it's gonna make something spiral inward, and then how can that be a circle? Like, it has some circular qualities to it, but it's not a perfect circle. So I have what is called my bad day scenario. It's a very bad day. I'm driving my car. No, I don't drive a green Bug. It's the only one I can find clip art wise. I'm driving my car along, and then out of nowhere, a car comes and hits me.
Did that thing honk?
It did honk.
It did honk.
That's really cool.
Here, I'll show it again, watch. It honks louder the second time. So imagine you're driving down Los Gatos Boulevard and somebody is driving down Blossom Hill and they hit you, and the hit is perpendicular to your direction of motion. So we're gonna represent this with an arrow. So go ahead and draw an arrow. If you have two different colors of pen handy, then you might want to use them. If you don't, you could just use two different line styles. That would work too.
You guys can reference if you want.
Got some what? These nuts. Yeah.
And this first blue arrow is showing my direction of motion, also known as a velocity vector.
Oh my God.
So this is the same color here. I don't have the same exact color as on the PowerPoint. So I've got my direction of motion. If I were going faster, this arrow would be longer. If I was going slower, it would be shorter. This is showing my motion. We're going to use a different color to show the force that I receive from the other vehicle that comes in.
Is it supposed to be like the same length? Oh, not shorter.
So there are two different arrows. One is showing a force. In this case, the net force, the unbalanced force, and the other showing my motion. One other thing that you probably want to make note of is that these two are perpendicular to each other, because those two streets were perpendicular. I'm driving one way, 90-degree angle, the car comes and hits me in the other direction. What do you think my new path is going to be once I receive this hit that's 90 degrees? Show me with your fingers. Point in the direction that you think this new arrow should be, and I see most of you making that direction. Good job. Okay, so now draw another arrow here.
Shouldn't it be, is it shorter than the first one?
It should be the same color because it's indicating your motion.
Gotcha.
Same color, that's my motion, and I like to say this is my bad day scenario.
You get.
Out of the blue, somebody else comes along and hits me.
Oh God.
It's probably Chloe driving.
Again, 90 degrees. Did you have an accident, Chloe?
No, I'm not about driver.
Okay.
She hit a deer.
I hit a deer. I think I told you that story.
I've never heard it.
Okay. So, I'm still driving, I'm still moving at the same speed that I was before, and I got hit, and what is my new direction of motion gonna be? Show me with your fingers.
25, like down.
Like that,
It's an octagon.
and it's a really, really bad day.
You get smacked.
You got shot?
You get smacked.
She got shot.
I said smacked.
And for some reason, I just don't stop.
You just, that's
I just keep going.
that's unsafe.
And I keep getting hit, and I keep getting hit, and I keep getting hit.
You got hit again?
Can we not draw?
Yes, you need to draw all of those.
Oh my god.
It's a circle.
It's a,
It's a circle. It's a circle. Isn't it actually?
yeah, that's more like an octagon.
So it is an octagon because I received 8 different hits.
Yikes.
Is it a circle?
No.
Is it a cycle?
Yes.
Yes. I have completed a cycle. I've come back to the same spot that I was before. How could I make it more circular?
Get hit like in between each
Get hit
one.
harder.
I could get continuous hits, more hits, infinite number of hits.
Jeez, what car are you driving?
Yeah.
An infinite number of hits would give me a more circular shape.
Gotcha.
So when we go back to our definition, the one that didn't seem to make a whole lot of sense at first, this continuous net force, if it wasn't continuous, it wouldn't be circular. If it was only 8 times, I'd have an octagon shape, not a circle shape. But the continuous net force allows me to have a circular or a curved shape. Now, what direction are all of those arrows?
In.
What direction are they all pointing?
Middle.
Toward the center of the circle. So, this idea of a continuous net force directed towards the center of the circle does not make me go in a spiral. It makes me go in a circle because I also have my own motion, my own momentum, or my own inertia that I need to keep in account for. So as I'm driving along, I keep driving the same exact speed, 30 miles per hour or whatever speed I was going, and I'm receiving continuous hits all along the way.
Yikes.
Now, again, I want to point out these are all 90 degrees to each other perpendicular. Did you put that into your diagram, that these are all 90 degrees? Do you have 2 different color arrows or 2 different style arrows, one showing the motion, one showing the net force? Now, I've gotten back to my original location here. Made it back. I didn't stop. I'm just like, I'm getting there. I'm going. I got to get to the same spot. And now there is no longer a net force there. So there's going to be a new definition here.
So you just go forward.
If I get rid of that force, that net force, there's nobody to hit me again. What's going to happen to my motion?
You'll move in a straight line.
I'm now able to move in a straight line path, and that straight line path happens to be tangent to the circle.
Oh.
A few weeks ago, we learned about what a line tangent to a circle or tangent to the curve looks like. So if this is my exact location that I'm at, and now there's not a net force to redirect me, I can go tangent to that circle, and I will drive off. Which is what happened when you picked up the hoop. Some of you figured out when to pick up the hoop so that you could make it go in a straight line and get the hoopla, or however many points you got. Some of you figured out that you needed to pull up the hoop at a certain point, but then maybe you didn't have the timing right, so maybe instead of releasing it at this point, maybe you released it over here, and then what direction would the ball go?
Out.
Point with your fingers. If I released it at this point, where would the ball go?
Up.
It would go something like that, because it's always going to be tangent to the circle. And then all of this is related to Newton's second law, which table 2 referred to. Newton's second law, they said that in the presence of a net force, the object will accelerate. And they said, oh, well, I know that if something had more mass, it took more force to get that ball to go in its circle. We're gonna write it slightly different for this unit. And the reason we write it slightly different for this unit is because now our accelerations are not like moving forward and slowing down or moving forward and speeding up. It's not about a change in speed. Now it's about a change in direction. When you took the ball and you were doing your little hoopla thing here, for the most part, the ball was going a constant speed as it went around the hoop. Would you agree that this ball is going at a constant speed around the hoop? If I were to measure the distance it took to go around one circle and how much time it took, it would probably be the same every single time. So my speed is not changing, but what's changing is the direction. At every instant in time, that ball is traveling in a new direction. So we use a different type of terminology to talk about this change in direction, and we use a little subscript C. This still means the net force. M obviously still means mass. And the A here is a centripetal acceleration. We'll talk more about what that word means next time. If you want to think C just for circle at this point, that's fine. So we have a circular acceleration. And you're like, but it's not changing speed. How can it accelerate? It's changing its direction. And then we have a center-seeking force. Again, we'll talk more about that next time. Don't worry so much about where this equation, v squared over r, comes from. Just know that we talked about this with respect to the hoopla. If something was going faster, that means it had a greater acceleration, which meant it took more force for that thing to get at that greater speed. Lily, you have a question? Yeah. We're going to practice using this equation in the lab also that we're doing next. There's one more slide, one more statement. So again, if you are not able to keep up on the notes, this will be posted on Canvas. The last thing you need to know about this acceleration is that the net force, we already said the net force is pointed towards the center of the circle. That means the acceleration is pointed towards the center of the circle as well, because accelerations and net forces act in the same direction. If I'm walking along and somebody comes from behind and pushes me, what direction am I going to speed up?
Forward.
I'll speed up forward. If I'm walking and somebody pulls back on me, what direction am I going to slow down?
Backward.
Backwards. So forces and accelerations happen in the same direction. So if the net force was going towards the center of that circle, so is the acceleration. The lab that we're going to do today, we are going to be measuring some accelerations. So I'm going to come around and I'm going to pass out the lab while you continue writing that. Chloe, you can stop
Are
the
we gonna
video.
finish the lab games or?